Happy asynchronous Wednesday, or maybe Thursday, everyone. I'm hoping you're doing well. Seniors, if you took your SAT, I'm hoping that went well. Also, sorry I'm giving you some work that we have to do. Today, you're going to be taking some notes with me on section 2.3, properties of functions. Some things will be familiar, some will not, but here we go. Got my title down, so if at any time I'm going too fast, you can pause your video and catch up. But I want to get through this, so let's see. Let's start. Number 1, average rate of change. Now, we've talked a little bit about this before, you might remember. This is going to be our slope. Delta y over delta x, the change in y over the change in x. If we're talking about a line, a linear function, lines have slope. The average rate of change is the slope. But then other functions, like parabolas, or root functions, or cube functions, and a lot of other functions, they don't have slope. But we can define the average rate of change between points. Average rate of change between points. So while other functions are not linear, we can take 2 points on them and draw a line through them. And the average rate of change is going to be the slope of the line connecting those 2 points. So let's take 2 points, a comma f of a, so meaning we have some x value a and we plug it into f of our function, and then our second point b comma f of b. So another x value, plug that in also to get that y value. The average rate of change is f of b minus f of a over b minus a. This is the same thing as our slope function. Maybe I'll write it down just to kind of hit home the point here. If we have on a linear function x1 comma y1 and x2 comma y2, our slope between those 2 points is y2 minus y1 over x2 minus x1. They're the same thing. Slope of a line and the average rate of change between 2 points, that's basically slope. So let's write this one more time. The average rate of change is the slope of the secant line. Now, I don't know how much you know about secant lines. There's a difference between what a secant line is and the function secant, the trig function secant. A secant line is a line that hits something twice. So I'm going to give you 2 quick sketches here. Let's take this graph and let's take this graph right there. So what is a secant line? A secant line is something that's going to hit through the graph twice, or sometimes more than just twice. But when we think about our secant line, we're going to think about it as saying like our a value is here, and this is a, f of a, and this would be our b value here, so this would be b comma f of b, the point on the... So we'd be taking the slope between these 2 points by drawing that line through them. So it'll look a little bit more straightforward here on this picture. This one, if I could draw straight, is the secant line. And this is different from, if you recall, a tangent line like this. So a tangent line touches something once, where a secant line will hit through it at least twice. We think about the 2 points that we're using. So let's jump into some problems with this here. Sorry about that wire. That's kind of ugly looking here. Ugh. Okay. So let's use the function f of x equals x squared minus 4x. Let's find the average rate of change from 2 to x. So what we need to do at this point is come up with our 2 points. We need our f of whatever. So let's take our 2, f of 2, and our x, f of x. Well, what is f of 2? We plug in 2 here. 2 squared is 4, minus 4 times 2. If I'm not mistaken, that is negative 4. I don't know where I wrote a negative 2 right there. 2 negative 4. And then f of x, I mean, we're told what f of x is. We can't plug in x, and I guess f of x is already plugged in. And look, I'm already making a mistake. It's x comma x squared minus 4x. That's what it is when we're done plugging in x. So how would we find the average rate of change? Well, we take f of b minus f of a, x squared minus 4x minus negative 4, over b minus a, x minus 2. Now, sometimes we're actually going to be able to simplify this. In this case, one of these problems is a lot that you'll see in class. If we factor the top, that's x minus 2 times x minus 2. That cancels with the x minus 2 in the bottom. So what's the average rate of change between 2 and x? It's the x minus 2. So we'll be getting numbers, or not numbers when we're not plugging, not just using numbers. We'll sometimes get a function to represent our average rate of change. All right, let's do one more. Let's find the slope of the secant line. From 2f of 2 to 4 f of 4. Now, I think this is something that should feel a little familiar. I'd love for you to pause, try this yourself, and then come back for the answer. So I'm actually going to pause. I'm going to write my answer. You do the same. Come back when you're ready. To do this problem, you need to evaluate the function at 2 and 4, get our 2 points, 2, negative 4, and 4 comma 0, and then find the slope between them. 0 minus negative 4 over 4 minus 2 simplifies to 2. Now what we're going to do here for not our final step, but our final kind of algebraic step, is now we're going to write the equation. I'll write the whole word. Write the equation of the secant line from part B. So from part B above. So how do we write linear functions? Well, we need slope and a point. Let's use point slope form. Let's make it easy on ourselves. And we have the slope, that's our average rate of change, the slope of the secant line. And we need a point. We actually have 2. Neither is the y-intercept, so it's not super fast to write it as or in slope-intercept form, but point slope form, we have 2 options immediately. Y minus the y coordinates, that would make that plus 4 equals the slope 2 times x minus the x coordinate 2. Or we can use the other point, 4 comma 0, y minus 0 equals 2 times x minus 4. Now if you wanted to write it in slope-intercept form, you could take either of these, kind of multiply everything out, move things from one side to the other, and both would simplify to y equals 2x minus 8. So any of those 3 is actually a good answer for this one. I'm going to draw you a quick sketch of kind of what the idea of this secant line is. So I'm going to pause and draw it, and then I'm going to explain it. So you'll probably have to pause it when you see my drawing in a second here. So one moment. So I kind of cheated. I grabbed some graph paper. Drawing our function and the secant line that we found. So you can see our function x squared minus 4x. You find its vertex would be at 2, negative 4. You find its x-intercept, it's at 0 and 4. The y-intercept is also at 0. It's a parabola. The secant line that we found for part C was going through the points 2, -, 4, and 4, 0. So I drew those 2 points there. I drew my straight line with a ruler that time, and we can see the line that goes through it. So this blue parabola right here, that doesn't have slope. We don't say that a quadratic has slope. But when we're looking for the average rate of change between 2 points, we draw a line through those 2 points, and the average rate of change is the slope of that line. So you can see that we found our slope to be 2. I guess you can't see that, that's off screen, but we go up 2 over 1, up 2 over 1. That's the slope of that line right there. All right, next thing that we're going to look at for properties of functions, we're going to talk about increasing, decreasing, and something called local extrema. So let's write it 2. Yeah, you can see it up there. So increasing and decreasing functions and local extrema. That's a fun word. So I'm going to draw a quick hand sketch of something that I wouldn't call necessarily a function itself. So let's draw. And again, you got to make noises when you're just drawing stuff like there. And let's draw this a little bit more straight and then down this way there. So draw a sketch like that. Let's put an arrow right there to signify that's going on forever. Let's label this point as -8, -3. Let's label this point right here -1, 2. Let's put a 1 next to that point right there. Let's make this point 3, 1, and finally let's make that 4 right there. So looking at this graph, let's talk about, first of all, our increasing and decreasing intervals. Now we've already done this a couple times, but I don't know if I've ever given it the explanation that it's needed yet. So when doing intervals and interval notation for increasing and decreasing, you can't be increasing at a point. So if you just look at one point, it's fixed. So when we write our intervals for this stuff, we never use brackets because we're never including a point, because a graph is never increasing at 2. It'd be increasing from 2 to something. So we don't use brackets. Looking at this, where's this graph increasing? If we kind of trace, I'm heading downwards till I get here. And from here to here, I am going up. So there is an increasing interval from -8 to -1. Notice parentheses, no brackets. I'm following along down, constant down, no more increasing. Looking at decreasing intervals, we start over here. This arrow signifies that this graph continues this way forever. So we would be decreasing all the way down to here at -8. So our first part is -infinity to -8. We start over on the left for infinity. We go over to -8 using only parentheses. We're increasing here. We're decreasing right there. -1 to 0. It's decreasing from there, that small part right there. Finally, this is constant, so that's not increasing or decreasing. And our final part is from 3 down. This arrow signifies forever. 3 to infinity. That is our decreasing interval. So it's 3 parts that we had to put together. Now let's talk about our local extrema. What are those? Local minimum, local maximum. What does the word local imply? Well, before I tell you, let me tell you, there's another word that is sometimes used. So you might actually hear me use it, relative. So this means the same thing as relative min or relative max. It just means that compared to kind of a window around this point, it is lower than everything around it or higher than everything around it. Sometimes a graph doesn't have a true maximum or minimum. Think about this graph right here. This goes up this way to the left forever. it's never going to reach its maximum point. There's always going to be something higher the further to the left of the graph you go. It's never going to have a true maximum. Down here on the right, it's going downwards forever. We would never be able to find a true minimum. This graph will continue going lower and lower and lower. But what the graph does have is local mins and local maxes. There's a point where you compare it to the stuff around it, and it's lower than all of that stuff. So take a look right here. When we compare this point to everything around it, it is lower than everything close to it. Even though we continue drawing this graph, and this point right here is lower, in its localness, in its window around it, this is lower than everything. This would be our local minimum. So the local minimum is the y value at a low point. Not the lowest. It doesn't have to be the lowest. It can be the lowest, but it doesn't have to be the lowest. It is just the low point. And that makes our local max, our y value, at a high point. So looking at this graph, this point right there is higher than everything around it. We would call 2 the local max, and it happens at -1. So let me write that. Local min of -3 at x equals -8. And this one is a local max of 2 at x equals -1. So the of is the value, the at is the where. The x coordinate is the where, the y value is the min or the max. We got one last thing to do. I'm going to write down the introduction here and pause for a second. I'll be right back. Our last topic for section 2.3 is even and odd functions. And this is going to seem a little familiar, but it's a little bit different than what we've already done. So let's start with our definition for even functions. For every x in the domain of whatever our function is f, there is also -x in the domain. Now that might not kind of tell you what an even function is, but this is going to help you identify things that are even functions. Even functions are symmetric with respect to the y-axis. So we've already talked a little bit about symmetry, so this should be a little familiar. And if you think back to what we talked about with symmetry, how did we test for y-axis symmetry? We took x, we replaced it with -x, and we got back to the same thing. So our definition for even functions takes that and uses function notation with it. Here is the definition of even functions, is that whenever you have f of x, just kidding, f of -x, when you take -x, plug it into the function, you get back out the exact same thing that you would if you plugged in just regular x. So I'll write the note. When we replace x with -x, there is no change. So we've already done that. Now we're giving it a nice formal definition in terms of even and odd functions. Odd functions, let's write down the definition for that. It's going to start off the exact same way. For every x in, sorry about that, the domain of f, there is also -x. And also replace y with -y. Again, maybe not the most helpful, so let's add some helpful things. Odd functions are symmetric with respect to the origin. Now thinking back to when we were talking about symmetry, How could we tell when something was symmetric with respect to the origin? When we replaced x with negative x and y with negative y, we got back to the same thing. So how do we write our definition for odd functions in function notation? When we replace x with negative x, right there, we got negative y. We replaced y with negative y, and we got back to the same thing. So how do we write this here? We write a negative on the outside of f of x because we sometimes can think about f of x as being kind of the output, the y coordinate. This is our place where it's replace y with negative y. So basically how I like to think about odd functions is when you plug in negative x, you get opposite of the original. You can basically take a negative, stick it out front, and in parentheses you get your f of x. Now, instead of just ending right here, I'm going to make this video just a little bit longer to go through a couple examples with you. Graphically, it's really easy to tell. If it's symmetric with the y-axis, it's even. If it's symmetric with the origin, it's odd. But let's take a look at some of our algebraic problems. So let's check for even or odd. Functions can be neither as well. I guess I should say that. Not all functions are even or odd. They don't have to be either. It can be neither. So how would we check this? Well, we would do f of negative x, and we would plug in negative x everywhere we see an x. If we get back out, if the negatives go away, it's even. If we can manipulate it somehow where I can write this original thing with a negative out front of all of it, it's odd. If I can't do either, it's neither. So negative x cubed is still negative x cubed, so let's write that as negative 4x cubed. Plus negative x we could do as minus x. Notice here, two negative signs. I'm going to factor out that negative sign. I'm going to put in parentheses 4x cubed plus x. What do we have here? We have a negative, and what's this whole thing? That's f of x. So what do we get? This is odd. When we're able to write the function kind of with a negative out front, it is odd. Let's do another example. Let's not pick one too easy, right? Yeah, whatever. Let's take f of x equals 2x to the fourth minus x squared plus the absolute value of x. So we start with plugging in negative x. So we get 2 negative x to the fourth minus negative x squared plus the absolute value of negative x. Well, negative x to the fourth, when you multiply something by itself 4 times, it's going to be positive no matter what. Same thing with squaring. You multiply it by itself twice, you're never going to send something negative, but that negative still stays. Don't forget that. And then when you take the absolute value of anything, it's always just going to be the positive thing. Sorry, I'm kind of writing sloppily here at the end. And when you look at this, what is this? That is exactly where we started. This is f of x. So when we plugged in f of negative x, we got f of x. So what can we say? This is even. I've run out of space, but I'd like to do a non-example. Wouldn't we like to see a non-example? I'll flip my paper over. Actually, I'll just write on the back here. You'll see some bleed through of our other work, but that's okay. I don't want to waste paper for just one more example here. So our last example of the day, sorry I made this video a little bit longer, but I wanted to show some actual problems. Let's take a look at the function g of x equals x squared plus the cube root of x. Let's do something like that. So we substitute in negative x. Negative x squared ends up being positive x squared no matter what. And then here, I don't know how much you know about cube roots, but when you take the cube root of like negative 8, it's negative 2. When you take the cube root of negative 27, it's negative 3. You get the negative answer. So this would be minus the cube root of x. This has a negative on one part but not both. We can't factor out a negative. There's nothing I can do to really change this just by the way it looks to get either g of x or negative g of x. We're not getting either. This cannot be manipulated in that way, so this one is a neither. As I kind of wrap up this video here for even and odd functions, the easiest way to kind of tell when things are even and odd is you got to be on the lookout for things that cancel negatives. Raising something to an even power makes negatives go away. Taking the square root sometimes makes negatives go away. Absolute values make negatives go away. When you see those kind of things, those parts help something be even. And if all the parts have that, yes, it's going to be even. Same thing for odd. Things that don't make negatives go away. Raising something to an odd power. Cube roots. It's not an odd power. It's close. It's like an odd power. When you see stuff like that, if all of the parts have those kind of things, you can tell it's odd. Like, I'll give you a little hint. If I saw y equals x to the 6th plus x to the 4th plus x squared plus 2, I know this is even. These even exponents and this thing without an exponent, all of that together are going to help make it even. If we had y equals x to the 5th plus x to the 3rd plus x, those are all odd exponents. I know that this is odd, and you can check with the graphs. It's going to work like that. The moment I add like a plus 8 to this, it's no longer odd. It'd be neither. Or if I added like an x squared, it's neither, because not everything is odd like that. But those are little hints to make this go faster sometimes for you to notice. So I went really long this time going over some examples. You got a Math Excel assignment to work on. This Friday, we're going to take a short quiz, 6 questions. Before we take it, we're going to have about a half hour of study time in class to make sure that we're ready for the quiz and you can ask all the questions that you need. We'll be doing some small group work and then coming together and asking me any answers that you need to make sure that you're well prepared, seeing as today might not be the most productive day for some of us if we had to take a standardized test, which we know aren't fun. So thank you for dealing with this long thing. Happy asynchronous day. I will see you all on Friday.